Thank you. Good morning, everybody. Right, so quick, I think this session is half an hour before coffee. So the topics we've got today before coffee, anyway, is the current HAMTV status, because people have noticed it's not on the air. So Ciaran's going to be talking about that, and then Phil is going to be talking about how the transport stream merger system. Then we're going to have a coffee break, and if we stay on time, that should be about half an hour. And then I'm going to talk about a Sail 2, the satellite that is going to be launched this year, so we're told, and is going to change the face of amateur radio and amateur television in Region 1. And then Dave's going to finish off with an update about the spectrum monitor that the BATC has been putting together so that we can all see what everybody else is doing, and everybody will be encouraged to behave themselves. So, as a starter then, HAMTV and Ciaran.
Okay. So, we're going to do a quick run through of what we're doing in space, the on-orbit capability. We've had quite a lot of changes this year, but I also want to go through some of the other things that are happening as well, such as very briefly talking about the live stream, which Phil's going to talk about afterwards. I'm going to talk about something called the Interoperable radio system, which is where the majority of our development attention has been focused this year. I'll give you an update on HAMTV, and then an intriguing project called Canister, which I don't know if many of you will have heard of it, but something that opens up some really interesting possibilities for us in the future. But first, I think this is the first time I've ever presented at a BATC meeting, and I wanted to acknowledge the phenomenal support I've had from BATC on all of the ARIS activities that we've been doing, the development of the web streaming, the professionalism of it all, and that's down to the likes of Noel, to Phil, to Frank, and to Peter Blakelow, actually, who was the very first member of BATC that I met, who agreed to stream my very first contact, which is almost exactly 10 years ago. So thank you very much to the BATC. So the live stream. One of the problems that we can sometimes get doing these contacts is that we always want to be able to give a URL out to somebody or to the wide world, to let people see what's going on in the schools. And very often we end up with live stream, Facebook, YouTube, all over the place. And one of the things that we've done, or as Phil has done actually, is to take it all together and develop the front end of live.aris.org, which is where we are certainly streaming all of our events to. We're starting to get some of the international teams to stream to it as well. And Phil has developed the capability of things like user tracking and everything else. So we can actually now start to give some metrics in terms of where the viewers are coming from around the world. And that sort of information is something that we actually do end up reporting upwards, back up to our main sponsors over in the US. And it keeps us going as the innovative things that we're also doing with space itself. So, the interoperable radio system. You're probably aware of the fact that we've got one radio system in Columbus and another radio system in the service module. The HAMTV unit is also in Columbus, but one of the problems that we have is that the power source for all of these different bits of equipment comes from multiple locations in Columbus. And one of the consequences of that is that if some of the experiments that are in the racks in Columbus are being carried out, we can lose power to devices such as the HAMTV unit. And that was certainly the case why in Principia we had, I think it was 7 in total, HAMTV contacts, because the other 3 times there were week-long or 2-week-long experiments running from ESA, which basically took the power away from us. So one of the things that the guys in the US have done is to come up with a concept of a single power supply. So instead of now having all of our different pieces of equipment powered from different sources, this one box will go in and will supply all our requirements for power in the future. It also means it's going to be permanently on, which means that we won't have this clash problem again in the future. The big benefit of this is that it's rated for the US segment and the Russian segment, so it can be used on either side. You might ask why that's the case. Well, one's 28 volts and the other one's 110 volts. So there's things in there to look after it. But it also means that we're finally getting to the point where we're starting to be able to standardize some of the equipment so that we can actually physically move it back and forth. For example, you may know that the Russian segment at the moment has got a D710, but the power setup for that is off the Russian power, which means we can't actually move it across to Columbus to make use of it. This will solve the problem for us. So a big development, and we are hoping to see this launch early 2019 itself. You'll also know that if you've tracked some of the ARIS contacts, that the audio from the Columbus module can sometimes be a little bit of a challenge. It's certainly a lot more than the recent contacts from the service module. The service module is pumping out about 50 watts on the D710. The good old Ericsson is pumping out between 3 and 5 watts at the moment. We're replacing that as well with a new D710, which will be set at 25 watts output. The whole unit, when it comes together, will then look a little bit like that. So we'll actually end up with the D710 base unit clamped onto the top of the power supply. All the airflow and everything has been taken care of, so we've got the airflow to do a sustained 25 watts on it as well. But that has taken some enormous effort to actually get to. It's been flight certified by NASA, but using volunteers from the ARIS team in the US, which is the first time we've done this. Normally the flight certification process ends up us paying somebody to do it for us, but that's quite expensive nowadays. So we trialed with NASA a program of actually doing the whole flight certification and safety certification ourselves, and it was tremendously successful. So, HAMTV. You've all seen some pictures. That's the unit in the bottom right-hand corner. We've had some really memorable times running HAMTV. Probably my favorite of all times is the one in the top left, which was our contact up in Otley. Absolutely cracking. The sheer impact of having the students in front and Tim waving behind, and that happened in a large number of, or 7 of the events that I said, and it was absolutely magical. The effect of Tim waving to a whole class or a hall full of school kids, and them just putting their hands up and waving back was just brilliant. But it was good. We did a lot of groundbreaking work with Tim in getting the concepts going and getting the concepts working. That was followed by Thomas Pesquet, by Paolo Nespoli, but also by some of the other American crew members as well, who have started to or carry out a few contacts. And another one of my favourites is top right there. That's Jack Fisher, who we did a chained HAMTV event, which was over Europe. It was a telebridge contact, but it was piping everything back over to the US, to Houston, to the Space Center, where one of the schools in Houston was actually organizing a space contact. And if you've ever been into the Space Center in Houston, there's a massive auditorium place itself with a massive screen at the back. We were projecting HAMTV onto that screen from Europe whilst in Houston with the Houston school talking to Jack Fisher all over the place. And it came down as a really phenomenal example of what we've managed to do as an international team. But all good fun. So where are we today? Like I said, being used successfully from 2016, from January 2016, right up to earlier this year. But it's broke, unfortunately. We have been trying to do some initial on-orbit investigations, but that's very limited because we don't necessarily have all the right equipment up there to do any tests. Any tests that we do set up, we have to be able to put down in procedures which then have to be vetted and verified. And the tests that we have done have been inconclusive. They haven't identified the problem. We've got a fairly good idea what some of the problems could be. It could be a simple fix, it could be a more complex fix, but we don't know. So what has been eventually decided is that we will downmass the HAMTV unit, bring it back to Earth, do some proper investigations, and then try and get it back up again. But there are a couple of problems with that. First off is that ownership rights with all the different equipment on the station is vested within different space agencies. So we've had to renegotiate and get permission for the HAMTV unit to be moved from one space agency to another space agency so they can downmass it for us. There's the issue of cost, that we still have to pay for a lot of this. But also we had a condition right at the beginning, which was that the original agreement was that it was an experimental HAMTV unit. If it failed or if there was a problem with it, the original intention was that we would send it back at a Progress vehicle. If you know what the Progress vehicles are, they do quite a nice light show in the sky whenever they're coming down. So we eventually got an agreement to move the unit from ESA to NASA so that we've got the capability to downmass it. Again, downmassing isn't the quickest of things because the actual manifests for each of the vehicles going up and coming down is worked out probably the best part of a year plus in advance. So we're hoping that the SpaceX vehicle that goes up in December, early December, will be the vehicle that, when it returns in January sometime, will be the one that brings the unit back down. The unit will then be sent across to Kaiser Italia, the developers of it, where we hope to get the fixes done that we need. We have to be careful on what fixes are applied so that we don't invalidate flight certification certificates. Quite what or which fixes are applied, I don't know yet. And then the expectation is that no earlier than sort of very late 2019, we expect to try and refly the unit. So at the moment, we're not looking at any HAMTV capability being available until at least 2020, which is unfortunate. However, that hasn't stopped the HAMTV community starting to get together. There's already ideas for HAMTV 2 in terms of an enhanced system, taking what we've learnt from HAMTV 1 and trying to better it and make it better for HAMTV 2. Key things are that what we want to do with it is very much get higher resolution available. We want to also make it potentially an uplink capability, so the crew has the ability to see the school and see the children asking the questions. That's one of the common requests we get back from the crew, is that the one thing they love, or the thing they love the most about Iris Contacts is just talking to children what they would really like is to be able to see them as well. So that's a long-term goal for us. And also, we want to make the unit such that we can replace key parts of it in space. So if we know, for example, the PA is gone, we can pull the PA out and plug a new one in. We want to be able to make it maneuverable across the segments as well. So there's lots of ideas, but as always, these things cost money. So we expect a few fundraising things coming out in the next year or so. And that leads us on to Canister, which is the main bit of work that's going on the space station with amateur radio at the moment, aside from school contacts. Canister is a project that's been developed by the Technical University of Berlin and by Martin Bucher, who's one of the professors there. Essentially, what it's doing is carrying out a spectrum survey over large parts of the Earth, many times during different times of day as well, and trying to identify what the spectrum usage is like. And it's doing this across a number of bands. It is fully integrated into the ARIS equipment. I've got a slide in a second to show you that. We got it commissioned just last month, and it's already started to deliver some data for the investigators. So what does it do? Essentially, it's a Lime SDR, a Lime Mini SDR, only set up in the receive mode. That was the quickest way we could actually get a Lime SDR flown. So transmit capability isn't there for us at the moment. It ties into all of the ARIS antennas on the Columbus module. We've made use of a coupler on the main VHF-UHF antennas, so we don't have to complicate procedures for the crew when they come to do an ARIS contact. It's just there all the time. Again, this is one of our goals of reducing the crew payload or the crew workload whenever they do things, and reduce the risk of equipment being left in the wrong state as well. We're using one of the AstroPi computers that went up there with Tim Peake, and that's basically given us our ground control stroke interface to the Lime SDR itself. As you can see, the ham units or the ham radio units are powered off one system. The AstroPi is powered off something else. The Lime SDR needs a little bit more of a boost than it can get from the AstroPi, so we've got power coming all over the place. So when we come to get the interoperable radio system in, we'll actually have a lot better control of it. So like I said, what it's doing, it's doing a analysis of the spectrum in a number of the bands, trying to do this in multiple locations around the world at multiple times of the day. They're producing, what they're producing out of it is effectively a heat map type thing of radio usage. They also have the capability of looking at LEO satellites, which are lower than the space station, and particularly the ones that get launched from the space station. So the primary objectives are the whole of that range. The secondary objectives of the mission is actually to look in the amateur, a really detailed bit into the amateur side, and especially the amateur satellite side, to get a really good understanding of what's going on, and if there are any interfering signals that we can try and identify from where in the world they're appearing. And also uniquely, something which will help us a lot is the assessment of the the antenna radiation pattern. You may be aware that we've got the the LS band patch antennas pointing downwards, nadar facing. and we've also got the VHF, UHF, dipole, not dipole, sorry, whip, that's it, thanks for the Graham, with one of the elements bent on it, so we have a particular problem when we're carrying out contacts using that antenna, because there are certain approach angles and elevations that actually give us real problems in schools. So this will give us a much, much better idea of what's going on. What does it look like? That. It's about that size. Absolutely cracking bit of kit. It's built using the same design as the Astra Pi's case itself, so it's an aluminium case with significant heat shield on the top. It's left running for as long as they have got access to the Astra Pi. And the key thing for us is what happens at the end of it. Well, Martin Buscher has been working with us and has worked really nicely with ARIS, and it has given us an inroad into working with more senior schools stroke universities. And what's going to happen is the Lime SDR will effectively be handed over to ARIS, and we then have the capability to do what we want with it. And our key goals here are then to sort of pull things together, get some experience of an SDR in space, which will be really helpful, especially moving forward to the deep space side of things. But it also means we've got an opportunity to implement some new functionality really, really quickly. Can we implement an LS-band repeater? Could we implement an L-band uplink so that we can deliver the picture of the schools going on to the astronauts? A lot more issues, and how on earth are we going to get the picture up there in the first place without desensing the S-band downlink? But it's all things that we're looking at. And of course, if you've got any ideas, we're always welcome or always open to hearing it. And there is and that's the logo for the Canister project. And there is actually a website which is more like a blog from Martin and his team. And there's some really good bits on it. He's starting to describe some of the information he's getting back from space. Really, really interesting. He's also stuck out a request there, so that if you've got high frequency capabilities, and by high frequency we mean into the gigahertz, he wants to look at potentially working with people to be able to send some power up to the station so that he can characterize what it looks like from the ground, or from space itself, so that he's got some basemark to work with. So in all, unfortunately not a great deal of HAMTV due to various equipment problems. An exciting problem or project that's going on at the moment, and a busy year coming up to try and get all the new equipment in and get it sorted. And that's it. Thank you very much.
Okay, unless there are any burning questions, we'll press on with Phil, if that's okay.
That would help.
Right, is that okay on the audio? Great. Okay, so I'm just going to talk a bit about the HAMTV. So a bit more of the technical details of the HAMTV transmitter from what Ciaran was saying. So it was product of a proposal in around 2000, 2001. Then when ESA launched the Columbus module up in 2008, there were a couple of ARIS SNL band antennas, which you've heard mentioned. So the transmitter was upmasked in 2013, and it has analog video and audio input, and then the output is DVB-S at about 2 megasymbols, so about 2 megabit with QPSK and a half FEC. and about 10 watts out. And of that 2 megabit, we've got about 900 kilobits of MPEG-2 video, 256 of audio, and then quite a bit of null padding in that as well, which is a bit of a controversial thing. And then, as Ciaran mentioned, that's connected up to the S-band patch antenna that's on the outside of Columbus, and it's sort of not quite pointing down so much as slightly sideways and slightly backwards, I think, which brings its own bit of fun. Again, as Ciaran mentioned, it was previously kept running as much as it could be with the sharing the power supply issues, which gave us something to tune up signals on. However, when the camera's not plugged in, it was just a black screen with a blue line down the left. We don't know why the blue line's there. And then system hiss on the audio, which wasn't very exciting to receive pass over pass. And also means you can't see whether the picture's breaking up or not, because the back screen doesn't really do anything. So it was a lot of listening to the audio and trying to listen for discontinuities in the audio. But when the astronaut plugs in the camera for the contact, we get a picture, as you've seen those two pictures before. So I'll skip over that bit. So the challenge of this really was that for these contacts who are quite often turning up 1 or 2 days before the contact at the school, getting the VHF station up and running with the FM audio, and getting an S-band dish up for this and aligning that for receiving the low Earth orbits. So basically parking Noel's Land Rover in the right compass orientation and getting everything so that when the master's put up, it would track properly. And of course, with 1 to 2 days, we've got maybe 4 or 5 passes maximum to get it working. So that doesn't leave much margin for getting it wrong. And then we've got the issue that we turn up there and there's a building that's obstructing part of the pass, or a tree, which isn't going to be much issue for the VHF side, but could cause the S-band to drop out. So with all these, for the first Principia contacts, we had a dish down at Goonhilly, which provided a backup. And then we streamed that as a backup feed, streamed the video over the internet to the venue to give us a backup in case anything happened with the receiver at the venue. We did also have a couple of times where there are a lot of spacecraft docked on the bottom of the ISS, and these stick out quite a lot from the bottom, and of course the patch antenna is right against the main bit. So at certain angles you're trying to look through a Soyuz or such, and of course the signal drops out at that point. But for someone 100 miles east of you, they've still got signal at that point. So certainly when we were doing some of the northern contacts, we had times when it dropped out for us and Goonhilly still had it, and then Goonhilly would drop out, but we still had it. And there was that selective obstruction going on there. So what we really wanted to do then was expand this, so get more ground stations involved, get more redundancy into it. But the whole point of this is to provide a feed for the school that they can wave at, and we want that to be as reliable as possible. So we have the receiver on site so they can see how we do it, but we also want to make sure that we can deliver the contact for that 10 minutes because we won't get a second chance. So the first thing that we had to go at was, well, this was set up, I'm not quite sure who set this up, but a multi-viewer. So we had different ground stations were streaming their video to these different players, and then someone sat in front of the players, and when one started playing, they maximized it onto the projector, and then when it had issues, they would minimize it, have a look at the others, and if there was another one that was doing it right, they'd then maximize that up to the projector. And it was a bit clunky, required someone to sit there and watch it, and really wasn't very nice. And so we started to think about better ways we could do this. So we started to dig into what is actually coming down. So we've got the DVB-S2 down, which has, DVB-S, which has the MPEG transport stream with the 188 byte packets. So each of those packets has its own CRC. That CRC is checked in Minitune. And using the UDP output from Minitune, we can basically get all the valid packets that are coming out of it. Now these we can then ideally assemble these packets from individual stations to make up a complete stream. We do have a bit of an issue though, that we have to synchronize the streams. Now there is a program clock reference timestamp that's in about every 1 in 50 packets. And in between that, there is a continuity counter between the packets. However, that only counts up to 16, I believe, and then rolls over. So if you miss about 20 packets, 20 of these 188 byte packets, then you have no idea whether there was a segment in the middle or whether there wasn't. So what we've done is we have an application on the ground station computers that runs alongside Minitune. The UDP output from Minitune goes into it. It gets these 188 byte packets in. It then filters, so we've got the different PIDs that come in, the video, the audio, a bit of metadata, and the null padding. And we filter that out so we just get the video and audio. Just the video and audio gets uploaded. We did have a bit of fun with that, where originally we were sending each packet up in its own UDP packet. And it turned out that as soon as you got signal lock, sometimes your router would crash because it's just suddenly delivering a lot of UDP packets at it. We're not quite sure why this happens, but it happened to quite a few people, and people ended up having to reboot their routers mid-pass. We now package 4 of these 188 bytes per UDP packet. That seems to have solved that, luckily. So the server then waits 100 milliseconds from a packet that comes in to give a window for other stations to upload. And it then assembles these here, and it lines them up on the PCR. So it picks a PCR, waits for the other ones to come in, tries to line it up on the PCR. If we haven't got that PCR packet, we can't really do anything with the stream from that station because we have no idea how it syncs up. But when it gets more than one like that, it'll then look for the next PCR packet and follow the most complete path through there. So ideally, we have ones like this where we can see that that goes to there, and then this syncs up so we can go from that to there. We then have an issue here where, because there isn't a complete path, even though we've got the data here, we don't have the timestamps to synchronize it. So we don't actually know if these 2 blocks are meant to be over here or meant to be over here. So we end up getting a bit of discontinuity here, and this is slightly annoying, but it's what we have to deal with in the DVBS. So this process runs in the middle, and this is a process, that Phil Heron developed. I asked him whether he had any ideas. He went back and looked at the spec and came up with this way of doing it. So it's a program call loop that runs on the server and takes these packets in, and then it produces an output buffer. So all of these that are selected get copied to an output buffer, and we end up with an output stream that contains the most complete copy that we can build up, basically. Another thing to mention was that, so the 100 millisecond buffer that we've got there, we had originally some issues with. So the Goonhilly dish has a very nice internet connection. It's about 5 millisecond latency. And then we had stations in France who didn't have very fast ADSL, and therefore were using 4G, and they tended to be up around 50, 60 milliseconds of latency. So in order to be able to combine the streams, we need that 100 millisecond window. However, that's 100 millisecond relative between the stations. So we have had success with Australian stations using this for their telebridge contacts, where their latency to the server is about 150 milliseconds, but because they all come in within about 20 or 30 milliseconds of each other, it's fine. It just operates 150 milliseconds delayed, and then they've got another 150 milliseconds for the video to get back, but in the end of it, it's 0.3 of a second, so nobody really notices. So we've got this core process that Phil Heron developed, and then this runs on the same server that runs the live.aris stream. And so we've got UDP inputs from each ground station, which is everyone piping their received MPEG-TS up. It pipes it up with a call sign ID, and then the server is pre-programmed to accept certain call sign IDs at the moment. And this is just so that it gets stuck in a slot, effectively. And the server is currently pre-programmed with slots. So if you go on the page at the moment, so this is live.aris.org/HAMTV, or you click on HAMTV at the top, and you've got, this screenshot has Goonhilly, Wouter in the Netherlands, Claudio, Leo, and then there's Jean-Pierre, Paul Marsh, and the Australian station's down at the bottom as well. So they all serve their feeds up on that. And then we have a bit of telemetry on what's going on here. As the packets go into the slot, we count the amount of packets that are coming in, and so this will display that it's receiving data from a given station on there. The other thing is, of course, we're recording the ID of the station that's being switched to in the segment, so that will flag up as a prime receiver on here as well. That can look a bit weird on that it sometimes selects multiple prime receivers at once, but actually because those PCR packets are 50 times a second, the merger can be switching 50 times a second. And we don't try and update this page 50 times a second. So it shows multiple sometimes, which confuses people a little. One of the other things we have with this is, I mentioned the latency and Goonhilly always coming in first. The application goes, when that 100 milliseconds is up, it then goes through the buffers that it's got data in, or the slots that it's got data in order to find the complete segment. And because Goonhilly currently has the best internet connection of anyone we've got connected, anyone else is welcome to try. Goonhilly will quite often get selected first if it's got it. And this has slightly annoyed people of when Goonhilly's got it perfectly, sometimes other people won't get a look in as being selected as prime receiver, even if they've got it for the complete pass as well. But that's just a case of the program deals with the first one that it received first, and that's nearly always Goonhilly. But it's great to have redundancy because, as I mentioned with our northern contacts, Goonhilly, as big as dish as it is, it can't see the signal through a Soyuz. So this then, the output comes out on a TCP stream, and we've had, that's available as a raw TCP of the MPEG-TS, and the idea is that that can be piped straight, or you can connect to that with VLC or such for the venue. And actually we've had quite a bit of success using the Raspberry Pi, connecting a TCP socket and then passing the MP2 video straight into the MPEG-2 hardware decoder on the Pi. And that has very minimal delay. So I've seen, it seems to be about 0.2 of a second from me uploading from Minitune to it going through the server, getting merged, coming back down, and actually being displayed on the TV that the Pi is plugged into. So I've had the Minitune video window and the Pi video, and there's about 0.2 of a second difference. So that's quite nice and real time. We have got there's about an 8-second delay on the HAMTV audio due to the encoder on the space side, which is not great, but this is trying to minimize the delay on our side, and hopefully, maybe in the next version, the encoder will have less delay on the space side. So on this page, you can also view the HAMTV output. That is done through HTML5 because everyone trying to connect over TCP, and we often have 300, 400 people on this during a contact. It would overload it a bit. So this is done with HTML5 video, which scales, which is what's being used for the live stream here and on the new BATC streamer. Subsequently, there's a bit of a delay, about 5 to 15 seconds extra delay on the public output of this. So this isn't the one that's used in the venue, this is the public output, which does mean that you'll see this pop up, someone will say receiving data, select as prime receiver, and then you have to sit there for 10 to 15 seconds before this actually shows any video. That's an unfortunate side effect of that, but it does still give you a way to watch the HAMTV. So Ciaran talked a bit about how it was used in contacts with those astronauts there. This is an example of it in action. So you've got Goonhilly receiving data my station receiving data, Jean-Pierre is receiving data, and Wouter is receiving data. And all of these are currently being used at some point. Jean-Pierre, unfortunately, has a high latency, and therefore, even though he's receiving, doesn't always get picked. But as well as using it as backup, Ciaran mentioned that was the Space Center contact in Houston, where because it was a telebridge with the ISS actually over Europe, the feed from the merger straight into, I believe they were using VLC for that on the display, that was their HAMTV feed. And that worked very well for them. Is there anything else? So I have slightly rushed through that, but has anyone got any questions on it? Yep.
In an earlier slide, there was a picture of one of the transmitter units. I forget which one, but it had a big heatsink on the top. And as convection doesn't work so well in zero gravity, I wondered why that heatsink wasn't black to improve the radiation.
Bring up the interoperable radio one.
Yeah. Sorry, that one.
That one. That's simply because if Dave, have you got the Astro Pi with you? I'll show you this in a second, but that's because the Astro Pi unit that has been developed is an enormous chunk of metal with an enormous heatsink on it, purely to meet the flight rules of touch temperatures. Okay, what happened was that's it. So that's what it actually looks like. That's an Astro Pi unit itself. What the Canister people did was they took the same CAD files and edited them to give the same concept for and the same design casing as for the Canister project, and part of it meant having a big heat shield. It's all down to touch temperatures.
Thank you. The other point is on the ISS, you're quite right about convection not working very well in microgravity, but the ISS is, the air is being moved continuously. There are fans, if you listen to the noise, the sound coming from there are fans running the whole time, and air is always moving, because that is actually another problem. Carbon dioxide tends to sink to the bottom, so you could go into a hole and find you've got nothing to breathe. So that is a big issue. But so generally, most heat sinks or most equipment have got fans built in as well. The actual power dissipated by the stuff that we're using there is not enough necessarily to use the fans. But the interoperable power supply has got a fan or 5 in it. Yeah. Yeah.
That's it. So we've got quite a lot of forced convection on the insides, but we've also got fans underneath the D710 blowing into it as well. And that's been one of the major areas of development and certification with the space agencies, that we've had to get that right. So it's mandated a few technical changes here and there, but generally that's what we've been working with.
Okay, any more questions, or can we go for coffee? No pressure at all.